Okay, I'm going to walk through this green space calculation. I'm going to break it up into 3 parts. In this first part, I'm going to just prep the data, and then we'll do the calculation and stuff in another little video thing to keep them short. Alright, so the idea here is you might be a city planner or a developer or a landscape architect, something like that, and we've got this area basically that we are interested in understanding the amount of green space. It might be for park planning or something like that. Proximity, how many people are being serviced by green space, something like that. So I give you this aerial image, which is the AOI, and it's got the RGB bands in it, and that's why you need to add this carefully to make sure that all 3 of these come in at the same time. The area of interest, this guy is a polygon feature class, and I just have no fill and an orange outline. That's basically a polygon that we're going to use for clipping later. The only reason I give you this area of interest shapefile, or this aerial image, is so that you can kind of see where the green spaces are and use it to test this TIFF that I gave you. So this has already been classified. There's a tool that you're going to run in part 2 called supervised image classification, and that is going to show you how you might generate something like this green space TIFF. But basically, you're looking at it and saying, okay, here's open area here, green foliage here, heart-shaped lake or something, so maybe that's not, but it does show up as green space. So we're just looking for a correlation so that you can evaluate these and decide for yourself if they're correct, and they are. But the first thing you need to do is go into the attribute table and ask yourself what value those cells actually hold. And for some reason they're given the value of 1 and 29. We can leave them this way if we want to, and it's actually completely fine to leave them this way, and maybe I'll just run it that way just to show you what I'm talking about. But we really want to just own up to the fact that there's a true and a false value here. We've got a green that we're going to consider true because that's what we're interested in, and then we have other. The second thing that we need is the DEM. Because for this setup, we're going to break it into elevation classes, and we just want to know what proportion of each elevation class is green or open space or foliage or something like that. It could be anything else you want to. It could be buffer proximities around housing densities. It could be city blocks or certain neighborhoods. Whatever your zones are, doesn't really matter. We're going to set up elevation zones just to do it, and just to give you the practice of classifying rasters one more time. But we definitely want to clip this. We've got a big rectangle, and we're not interested in elevation classes that are outside this area of interest, so we're going to use this polygon shape to cut it. Now, you could use this shape to cut it. You can cut a raster with a raster. So we could cut this DEM, the black and white thing, with this aerial image. But what it does when you're dealing with rasters as cutting tools is it just takes a rectangle, basically this shape. So that's what I did with a larger DEM. I clipped it using this area of interest raster. It takes the maximum and minimum northing, and it takes the maximum and minimum easting, and it just creates a rectangular box defined by those 4 coordinates, and that's what it uses to clip. If we use a clipping with the clipping tool, if we use a polygon, it allows us to do that. Let me show you. It allows you to use the geometry of the vector feature. So we want data management because we're cutting a raster. The analysis tool would allow you to cut just vector data. So your input raster is going to be your DEM. The output extent, so this is the extent that we want our output to be. So in other words, the raster dataset or feature class used as the extent. So always use this if you have questions. The tool help, hide help. You can click on any one of these things and it defines what it's talking about. Output raster dataset, the name, location for the data you're creating. So the output extent is what we want to define our clipping, basically our cookie cutter. And if we use, like I said, this area of interest here, then this becomes active. This is the rectangle that would be defined by the min-max easting and northings, or we can use the geometry to clip it, and that's what we want to do. We want to use this actual shape. So We need to get that done. I did it and called it drape clip, which is this thing. And if I turn off my area of interest, you can see I've isolated the DEM just within my area of interest. So we don't need this anymore. We technically don't need this anymore. We just want to be working with our clip. And we don't need this anymore. This is the area of interest. Remember, it's the aerial image. It's basically just there to use as a guide so you can evaluate your work. We really want this and this. So we have somebody has already classified the green space for you, and we have our elevations. So let's run the reclassify of the elevations first. And spatial analysis is what it is. And is it going to open? Yes, it is eventually. Okay, so we want our clipped draper DEM, whatever you call it. I can't remember what I suggested that you call it, but there you have it. We're going to use the classify button to set it up the way we want, and we want it to have defined intervals because we want them to be 20-meter classes, and so our interval size is going to be 20. The units here are always associated with the data set itself. And then if I hit OK, now it has set up 20-meter classes, and there should be about 10 of them. Yep. And then what we want to do is just give them a value that's going to help us relate it back. You can leave it as 1 through 10, but then it's going to be up to you to remember that the first class is the one that ended at 1420. And so I think it's easier to just put that code in here. 1440, whoopsie, 1460, 1480, 1500. I'm just using the down arrow. And, oh, that was 1560. Those of you who don't know me know that I'm nearly blind. Okay, or that know me, that know that I'm blind. Okay, so there we have it. No data is going to be no data. We're going to put it someplace legitimate so we can find it again. And I'll just call it test, but you should probably name it something better, like draper DEM or DEM 20-meter or DEM class for classified, something that allows you to know that it's the draper DEM, it's been classified, so you can find it later. I have geoprocessing set up to run in the foreground. I can show you how to do that. For some reason, ARC likes to error out every once in a while if you have geoprocessing run in the background. Okay, so what I was saying is that ARC has a couple tools or functions that are erroring out in 10.3. I don't know if they fixed it in 10.4, but the error that you get alludes to geoprocessing in the background. This is something that changed when they brought 10 out. If you go up to your geoprocessing drop down and go to geoprocessing options, I uncheck this box to enable background processing. I like to sit and wait when tools are running because I don't trust ARC to be able to handle too many things at once. So I disenable background processing and force all the tools to run right in the foreground, and I literally have to wait for them to finish, and I have to close the results box. I trust ARC better that way, which I guess means I don't trust ARC. So there you have it. So these are the results, and this is what it should typically look like. You've got these 10 classes, they're 20-meter classes, we're calling them, their highest elevation of that class, and there you have it. So if we look in the attribute table, this is the kind of the nuts and bolts of it. We have a value class of 1420, and that was everything from around 1400 up. There's 1701 cells in that class. It must be this really little baby down here. Okay, so you kind of want to take a look at these, just make sure it makes sense, and it pretty much does, I think. Now, if we go into the green space attribute table, remember we have values of 1 and 29. So just ask yourself what would happen. If we have a bunch of cells that have been assigned the value of 1420, and we add it to this data set, if we add this one to this one, if the two data sets line up with each other, and each raster cell is sitting, directly above the one that corresponds from this data set. So the locations are the exact same and the cell sizes are the same size and they line up properly. Then it should be a really easy thing to conceptualize that if at a location in this cell, in this class, sorry, if the green space is green, then the output value is going to be 1421. If it's not green, it's going to be 1449 because we're adding 29 to 1420. And so our output feature class, or sorry, our output raster is going to have cell values of 1421, 1449, 1441, 1469, 1461, 1489. Does that make sense? That's what you would expect the output raster to have. And if it doesn't, then something's wrong. So I think I have you guys do this a couple times from here out to the end of the semester because this is a huge way that we run really basic models in ARC. And there is a way to add more interesting things together than just kind of binary true-false things. And we'll get into that in the part 3 a little tiny bit, but this is kind of a fun way to model in ARC. So I'm going to quit right there. What we'll do next is make sure that our environments are set correctly so that we are making sure that these two have the same size and are aligned, cell size and are aligned.